What if a single AI model could generate a physics accurate, consistent video just from a text prompt or an image input? What if that same model you use could reason on an image or a video and tell you information about that and think about how it will play out in the real world? Even better yet, what that same model was able to predict a future video of an action for a robot, but also generate the action sequence, the motor control data for that robot to play it out in real life. Well, that does exist. That's what NVIDIA is now calling Cosmos 3. That is the newest version of Cosmos. And they're taking all of these different components, these different frameworks that they've built, and they're putting it into one model and one framework. And I'm really excited to get my hands on it in this video. And we're going to see how it works. I'm focusing on robotics. So let's get into it. But before we get our hands on Cosmos 3, I just wanted to first talk about how they're using a mixture of transformers architecture. So this is new. There's an autoregressive and a diffusion tower. You have your autoregressive reasoner tower, which is here, and that's basically reasoning on what it sees, on its actions. And then it has this diffusion generator where it generates its output. So, it's going to reason on text, image, video, audio, and action. And then it's going to generate text, image, video, audio, and actions. So it goes through a two-step mixture transformer. It is fast, much faster than the last one. And this is really one, like you could say, one checkpoint, 5 models. You have a world generation model, which is text to image, image to video, text to video. You have a VLM, your vision language model, which will reason and then tell you what's happening. It has 4 dynamics. So that is basically telling you, like, you give it some action and it will tell you what's going to simulate next. And because it's like a world simulator. And then you have inverse dynamics, which will work its way backwards. And then a policy model, which is more like your world action model here, where it's like, hey, here is a scene, here's an action, generate a video of what's going to happen next and the action control state for that model. And then it's available in 2 different size models. You have the Nano and the Super. I do have the metrics on the size of Nano versus Super. For Super, it's a 64 billion parameter model. That's 32 billion in the reasoner and 32 billion in the generator tower. The Nano is a 16 billion parameter model. Again, and that's like 8 and 8, 8 in the reasoner, 8 in the generator. So they split them half and half. So again, 16 billion parameters is a much smaller model than running the 64 billion parameters. But neither of these are extremely large models. With that, we're going to do a little hands-on demo, and I will make sure in the description of this video, I will link the GitHub repository so you can start playing with Cosmos 3 yourself. There is a Hugging Face model page as well. I'll make sure I link that as well. So when you go to the Hugging Face page, you can then download those checkpoints. And always as I go along, if you do have questions, put them in the comments. You can always relay them to NVIDIA for help, or I'll be able to answer them myself. I will not be referring to my own forked version of the GitHub. We'll just be using the pre-release that they gave me access to, but by now the full release should be out for you to use today. So the first thing you'll notice is I'm on a Mac, which is because I'm going to be running this using Brev, because it's much faster than running it local inference. Even on my Spark actually took a while to run inference. It works great. I also ran this on my 6000 ADA with the Omni, the Nano, the smaller model. It will run with some offloading, but it still took a while. So I want to show you guys how you would typically run Cosmos, which is using some sort of cloud service. Before I get there, let's start just a little bit on just how to get this thing installed. Again, I'm looking at a pre-release, but the instructions should be somewhat similar when the actual version is released. It is super easy. You just install some dependencies. Again, I did this in Brev. I just started up an instance with an H100 because I wanted that speed. And then I made sure I had CUDA 13. And then you're just going to use UV sync. And then you're going to activate your environment. And then everything's really ready to go. Before we also get too far into this, I do want to point out they actually include an agents markdown file. That's right. They built this with agents in mind. So a future video that I may be doing is having an agent use Cosmos to set up a JSON file, run the training, provide the files. This is a great way to actually use this because as we move forward, you will see that I'm shuffling a lot of files around, and ideally an agent can do this all for you. You don't actually have to be sitting here typing in commands, changing in JSON. So with that in mind, just remember, this is an agentic workflow first. Now let's get into this. So I'm just gonna show you, here I am. I'm actually in Brev. You can see here, and I'm also have activated my content environment. You can see that I'm running an H100. I think Nebius is the provider. It all runs really fast. We're talking about a few minutes per generation versus tens of minutes, like looking easily at 20 plus minutes per generation on my Ada, and even slower on the Spark. So here I am in here. One thing I like to do when I run Brev is you can go to here, you can hit Brev, open, and I called my environment Cosmos, and it will, I think it already is open, but it will open it up in VS Code. For what I'm doing today, VS Code might not be the way you want to go, but it is an easy way to look at all your code, see all of your files. You can even drag and drop some files when you're just testing. Again, if you're doing this deployment, you wouldn't be sitting here interfacing this way. But we're going to start out by running a few tests. We're going to do the text to video first, and they have some set up in here. So if you go and you look in the file structure, you have your Cosmos, and you will have there'll be a folder where they have a bunch of different inputs, and we're going to use the Omni model, and they have this image to video, different ones. We're going to do text to video right here, and you'll see there's not much to it. We have like a model name, a name of your test. And so we'll call this text to video, I don't know, test one, like that, and a prompt. And I kind of have a prompt in here. Okay, so I have word wrap. It's kind of like a long prompt. I actually have a few we're gonna try. So the first one I'm gonna do is like a third person robot, and it's going to be like that. It's gonna be sorting some packages, nothing too crazy. We'll see as a conveyor, some overhead LED lights. So you just give it a really good idea of what you want it to look like as my prompt. And then if I just want to run this is, again, very easy. I'm going to go back to my terminal session, like so, where I'm in here. And they give you some prompt guides. So if I actually went back to setup here, they actually have a quick start file in their docs that will kind of tell you how to run it. Here's inference. It'll tell you basically, how to run it. It's just Python. You're going to bring up the framework scripts inference. Parallelism. I'm going to be running this parallelism preset to latency. You can read what that means. Then you're going to input that JSON. So it's the JSON file that basically tells it what to do, where to output, and so forth. So I'm basically just going to run that. Okay, so I'm just going to put in this prompt. So basically you're just going to run Python. You tell it to run that inference script, that parallelism preset. There's two different presets. You can look into the different ones. This is the one they recommend. You have your input file, which I had that t2v.json. My output, it'll go in this outputs Omni Nano folder because that's what I'm running as. Path to my checkpoints. So I have downloaded checkpoints. Again, when you're setting this up, this one thing it'll take a little bit of time is you got to download, a few, like over 100 gigabytes of checkpoints, but that goes pretty quick on Brev. And then a seed, and you can change your seed, but that's for reproducibility. We could put a random seed in there. I'm just gonna leave that, and I'm gonna hit enter, and this will run. And so I'm gonna fast forward this video, but I did want to show you the output of the console so you can get an idea of what it showed and how fast it ran. As you can see, it's already doing things. Just a little FYI, the first time you do run this, it takes a little bit longer because it has to download some additional checkpoints. But once those are downloaded, things go really quick, additional time. So here we are, we're already sampling. I think if I move my head out of the way, Just so you know, once it's sampling, that's kind of like the last step. That takes about 3.5 minutes on this PC or on Brev. And it takes about 20 something minutes on my Ada. So this is a much faster way to go. So let me just jump down to when this is done. Okay, so now it's done. Again, maybe I'll move my head up here. You'll see that it's at 3 minutes and 29 seconds. So again, this is fairly quick on an H100. You could even go up to a larger GPU compute, but that's pretty quick. Does 5.98 seconds per iteration. So I was seeing on the Spark about 100 seconds per iteration. To give you an idea, it's like 20 times slower. So not ideal for running Cosmos. It does work though. So good if you want to test it out before you want to deploy here on the cloud and kind of know what you're doing before you actually have to release. So here we are. So now we're going to go see what our outputs are. That's why Visual Studio is really easy for. So now I can go here and I can go to my output, click on the vision output. It should be a video. Okay, here's the video. Again, it was supposed to be an egocentric view of like robots sorting packages. You can kind of see it there on the corner there. We have some others. It probably comes down to the strength of my prompt of how well this does. I'll show you another one I did actually, just to give you an idea. This is an earlier test as well. Again, we're going to keep this robotics focused. And this one was robot arms picking specific fruits and placing them into a bag. The model sometimes does make some mistakes. It was supposed to be on the left. This arm does not move, which did great. The fruit was actually in the order I told it to be. And then it was supposed to be the right arm picking fruit. And it had two arms on the right. But that happens. So that's why you want to test out different seeds. And if you can post-train on specific models of your robot, you will get better output because it has a better idea of what your robot arms look like and how they work. But it's amazing. This actually, I did get some great results. And so I'll run a couple more and show you the outputs. Just know they all take about the same amount of time. This is just text to video. You can input a video and it'll predict additional video footage after the end of it. You can input an image. There's different things. So here we go. This is really cool. It is from the gripper's point of view. It picks up that block and drops it back in. So it's supposed to be a cluttered workbench. It finds that colored block, and there you go. So this is where I see this could be really powerful, is that you want to make additional observation data for a robot. Maybe you just want to even come up with an idea. If you seed it with an actual image or video, I think it does a much better job. I just want to show you, like, it doesn't understand a wrist camera first-person view from a robot, which is pretty impressive that it was even able to figure that out. And it picked up an object. I showed another one that was picking up fruit. That was a highly curated scene where the actual fruit was said on the left. You had apples. In the middle, you had bananas. You had wood boxes. Just off text, it's able to come up with a scene that's very representative of what you're looking for. So if you're just trying to get some initial test data, text to video is great. Again, though, if you use an image or a video as your to seed with a prompt as well, you may get better mileage. But this is a great way just to do an initial test to see how well it can output a video. Does it look like real life? I liked when it picked up that block, that other blocks fall like you have real physics. And that's what we should expect from this. So from here, what's next? Well, there's different models, and I said I was going to test the ones that are more robotics focused. We're going to do the forward dynamics next. I'm just going to read what that is. This predicts the future video from a given observation image or video, text prompt, and action sequence. This plays an important role in modeling by generating the world that looks like from the system. But what it does is I'm going to give it a video and an action sequence. So that's like the control state of the arms, where it is. And I'm going to give it a text prompt of what it's supposed to do. And it's just going to use the very start of the video and then the additional action sequence. So basically, we're going to say, here's kind of what the scene looks like. Here's what the state of the arm is of the robot and what it's supposed to be doing. Produce the remaining video for that. So think about that as like perhaps you have a video of a robot and its arm is moving towards a block, and then you actually have all the sequence data to go pick up the rest of that block and move it. But you can have it render out a video. So let's go show you what that looks like. I'm going to actually use their example, and I'll tell you why as I run through this really quick. Okay, so let's first look at what the sample looks like. It says action for dynamics robot test. We're gonna run that one. You have this vision path here and an action path. So let's just take a look at what that looks like. There we go. It's grabbing that. It just grabs the pot and that's it. And then it has an action path. So it's basically saying what to do next. And the prompt will say, put the pot to the left of the purple item. This video is captured from first person perspective, looking at the scene. That's kind of like what we saw. You give it a number of steps, guidance. You can read how to modify these, your action chunk size. And it's using the bridge, the original bridge, the robot model. So you can't just run this on anything. The reason why I'm using their demo is because you have to use some of the models they have already for different robots. So it's using this specific robot model. So if you want to use your own model, you need to train on your own model. And so now from this, we have the JSON set up. You saw the video and we're going to run it and we're going to see what the output looks like. So from there to run inference, it's very much just like what we did with the text to video. Put this in to run it. Again, it's just like Python, same inference script, same parallelism preset as latency. We're just changing the input here. The output will always be the same. And then we'll just hit enter and we'll run. Again, you'll find this actually runs really quickly as well. Once you have all the checkpoints and stuff have been already preloaded into your computer, you'll see these things run pretty quick. As you see, it's already going. So let me just fast forward to the end and I'll give you an idea how long this took. Okay, it's all done. It actually runs, I think, faster. It says 8 seconds to run sampling. Everything else went pretty quick. Let's take a look at the output, and then it should output a video. Okay, there it goes. It grabs it, and I noticed that it stops just short. So this is something I need to work on. Okay, so I'm mid-edit here, and I got great feedback from the team at NVIDIA about the forward dynamics and how I was not sure that the output was correct. And they actually helped me understand what we're looking at here. So what it does is it takes the first frame from that video I originally showed you, which I'm putting on the screen here. And from there, it takes my prompt and the action sequence that I gave it, and then generates the video of what that would look like moving forward. So it actually, the reason why I was confused is because the output was so like the ground truth video that I didn't realize that it was different. So it basically just outputted a new video that looks almost identical to the original one, which is what we want. So looking back at this result is exactly what you need. So what you're doing is you're giving it, again, basically an image starting, a prompt, and the control state. What is the action of that robot arm? It's going to play that out for you. It's going to generate the video. And that way you could simulate a bunch of different arm states to do that in simulation. And then you could actually render what it looks like in real life from this, which is pretty cool. So anyways, I'm going to get back to the video. I just wanted to clear that up. What we've seen here is exactly what we expect and is a really good output. This next one I'm going to show you, which I'm going to pull on my screen, is a universal robot arm, and it's going to want to close a drawer. And so what you're doing in the policy model is you're giving it an observation, a text prompt, and then it will generate the rest of the video and the action sequence. So like, what is that control state of that arm? So let me just pull that up. Okay, so here it is. This is slow. So it's the robot. This is like the ground truth. So what it is, this is playing 24 frames per second, but it is going to close that white drawer. And that's what we want it to do. And when I'm going to run this model, this policy model, it's only going to ingest like the first few seconds of what you just saw, or actually the first second. So it's going to see up from here to there. So it doesn't really know how to complete that. It just shows that the arm's moving towards it. And that is going to be our prompt. So again, let's go look at that one. So we're going to run the policy model, which I called the urpolicytest.json. I made a brand new JSON. The model name. Okay, so we're going to run the policy model. Domain name. Again, that domain, you have to have specific robot. So I had to use this robot arm. There's a whole list of robots they've already trained data on. And if you're not using that same set of robots, you need to do some your own post-training. But so I just picked an observation from a robot they knew they had. A vision path. So that was that video I showed you. that is just sitting in the inputs folder. You can see it right there underneath there. Your prompt is close the white drawer. Super simple. I don't want it to do too much. Image size 480 frames per second. So it only runs at 5 frames per second. That's to optimize this. I know that's what we're used to. It was an ego view, action chunk size 16 here, seed, and then we're gonna the UR policy test output. So again, running this is just like the last several. So if I was to go back to terminal and basically just pull up what I already had, you're basically going to run this again. You're just going to go change your inputs. Nothing special. Every time you run this, it's super easy. You just got to change your input so it grabs the right JSON, which will tell it which model and stuff. I'm going to skip showing that because I just want to get down to you can see what the results are, because this one's really exciting. So I ran that. Again, it took maybe a minute. It goes really fast. And so now if I go to my outputs, here's my policy test. Again, you saw how that robot did everything in like 24 frames per second. We end up with this output video. Again, it's a low resolution video, but you'll see it goes and bam, it closed the drawer. And in a way I expected. Nothing looked off. That drawer closed. It's what I expect. It even like wobbles a little bit. You can even see like the top. So that's a good output, but it also gives you this. This is the sample outputs.json. You'll see here it has a little bit of a header, and then here's your control state data over time. And so if you were actually to even like rebuild the scene in Sim, you could put that state data in, or you could load that into your robot and see if that's correct. I didn't have a visual for that, but I did mock this up and it did it as expected. And so not only you got the video, you actually got that state data. So then you can deploy that to your robot in real life and see how well it does. So I hope that makes sense. We ran the text to video prompt, we ran the forward dynamics model, and we ran the policy model. And to me, the most interesting things, I like the text to video. It's always fun to play with, and image to video prompts always great. It's great if you just want to predict a future. Maybe you want to make 10 of those. You can even change like what the scene looks like, and it does reasoning in the background. Again, it's got this 2-tower infrastructure, but the policy one to me is most important for what you're doing here, because with a really quick time frame, I mean, that was really fast. You're able to create a visual and the control state data, the action data of that arm. So I'm not just getting visuals, I'm actually getting what that arm should be doing over time. And then you can deploy that onto a real robot arm, see how it works. And that's where you're going to start to see these gains, because in real life, everything works at like a 1-to-1. So if I capture things at 1-to-1, you end up with your time. I do 1 hour of robot manipulation, I get 1 hour of data. In this, we can tell it to come up with a ton of variety. Change up your seeds. Each one will be a little bit different, and you can then just run that and get a bunch more observation data really fast. So that's really exciting. So the last thing I want to jump into before we conclude this video is I actually wanted to show you guys the benchmarks, because I think the benchmarks are a really interesting part about this as well. And I'm just going to read what I have written down about this benchmark, because I don't want to spoil these words. This is the benchmarking when it comes to actually deploying is very important. So this is the #1 open foundation model on more than 8 public leaderboards. So that's 8 public leaderboards. This is at launch, and because leaderboards will change, but they are spanning the physics and domain accuracy for video generation, embodiment video generation success, anomaly detection reasoning, vision and AI reasoning, robot manipulation policy success. So it's not just that they got #1 in like one thing, it's that they were #1 for an open model on several different benchmarks. So let's just dive in a couple of those benchmarks and I'll show them off. Again, these are pre-release benchmarks, and so they will only get better from here. Okay, so here's just a few of the leaderboards. I'm just going to show you where they land. So the Cosmos 3 super model on the Vantage bench is #1. Here you go. You can see that overall it is beating even Gemini 3.1 Pro. The Nano model is smaller, but just underneath the Nano 3 Pro overall, which is very impressive. You can see that the Reason 2B is definitely an improvement over the prior models. So again, this is open. It is overall beating. You can jump into these leaderboards and look right now. And then as well on the 2026 AI City Challenge, the Cosmos 3 Super and Nano mean scores are beating out everything else. So that's really impressive on the model for visioning reasoning. So that is just how well is it reasoning on what it's seen, which is kind of the first step whenever you look at these things you need to know. The next one is the open model for world generation with the highest physics accuracy. So again, we're going to look at the physics accuracy, how well it's doing there. We have different leaderboards on the R bench. It's really hard to see. I can zoom in. I will try to put this bigger on my screen, but you can see Nano and Super are here again at the top, beating out Genesis 2.5, 2.2. The physical AI bench leaderboard, again, Super and Nano at the top. It's just really impressive that this open model is beating out everything else. And then here's one more leaderboard here. This is the physics IQ bench. You'll see again, it's at the top. For artificial analysis, again, we have a text to image leaderboard. It is again at the top here with the Super. The Super model will get you the best results. If again you're running this on Brev, you're running this on a model, a larger server, this will run just fine. And then the image to video leaderboard here as well. You're still at the top. So it's just impressive how many leaderboards you are. And then for robot policy, Cosmos 3 Nano policy, which is what I ran, again, top of the leaderboard, beating out Dream 0, Pi 05 Droid. There's some ones you've seen here that you will know. It is just quite impressive what we've got. Just all these leaderboards that they are on the top of. So with that, it's just saying that this model is not just like a single model. It is, as we said at the start, it's like a mix of transformers. It's got two towers. It's got your reasoner, and then it's got your generator. It's hard to call this just like a world model. It's not just creating videos. It's creating a world action model. It is a multiple models kind of in one framework. So think of it as a framework, and it's really impressive. Again, we didn't even talk really about the reasoner. We didn't run just video analysis. There's a lot of things you could do here. I tried just to focus on what robotics we would be using for additional use cases. So this is easy to get going. You can start pulling the code. I suggest running on Brev on an H100 if you want to move fast. If you want to save a few dollars, you can run on an A100 as well. You will do best if you have that like 90 something gigabytes of RAM. I also if you have an RTX 6000 Pro, that should also be a great desktop if you want to run it. But again, know that it won't run as fast. And again, you're only a few dollars an hour on Brev. So that is a good option. Even if you're testing it in a day, you're not going to spend probably more than $30 on credits if you spend all day on that. So a great way to test it. It runs fast. It is a very flexible model. The instructions are very clear. To invoke any inference is very easy. You just have to set up your JSON properly, and there's lots of information on how to set those all up. And again, if you want to see more of this Cosmos content, I will be doing more of it. Make sure you subscribe to my channel, and I will see you guys in the next video.